at the Genome Institute of Singapore A-Star and also at the University of Zagreb, where he also got his PhD in 2008. His research focuses on both classical and machine learning methods for genome assembly and also for foundation models for RNA and DNA. So please join me in welcoming Milev for his talk. Yeah.
I would like to thank organizers to inviting me. So, I will talk about RNA, but I will start talking about AlphaFold 2 and proteins. So, yeah, it was a huge success, and as all of us know, but still there are critics. So, it is not folding problem which was solved. It is actually the final fold. And also, there are sorry. So, if we have some mutations, then the AlphaFold can neglect them and provide incorrect structure. But can you imagine that we try to do the same for RNA and taking into account that we have almost 2 orders of magnitude less data? Okay. I'm told so. It is, yeah. So you know, people in Croatia like sports, like basketball, soccer, and all of this. So we're usually told, and I'm not talented for sport. So I decided science. So when we think about how to approach some problems, I really like the philosopher Daniel Dennett, who mentioned about the greedy reductionists. So sometimes we really try to simplify some problems without doing some necessary steps. So especially for RNA folding, trying to approach everything is not possible, and we will need lots of time and many dirty tricks to come to the right solutions. As I mentioned, there are 2 orders of magnitude less RNA structures than we have for proteins. So there may be, we usually, when we train models, we use around 1,000 on RNA sequences. And also, as I coming from DNA assembly field, so when we talked with many computer scientists, theoretical computer scientists, they found that all of our problems are NP hard, and they just moved. But now, we can resolve human genome, telomere to telomere, diploid genomes, with just a few errors. And I believe that it is possible for RNA to try to learn something. So I'm just trying to be optimistic. Okay, so if you look for RNA chains, so what is the expectation that we will come close to proteins? So for AlphaFold 2, they had 150,000 protein structures. If you look just RNA chains, which are not in some complexes, the number of structures resolved per year is about 100. So can you imagine how many years we need actually to come close to proteins? So we need to do something to move this field forward, and we need to do something in some smart way and trying to see. And also, we should be aware that most of these RNAs are ribosomal RNAs, tRNAs, riboswitches, and viral RNA, and there are just a few mRNAs. So what we can do? The idea people had maybe 10, 15 years ago was trying to produce this structural probing data. The most famous are SHAPE and DMS, and there are some other techniques, and we can produce them in the large numbers. So can they help us? So what that kind of data tell us? They tell us if some parts of RNAs are flexible or not. Sometimes we can say, okay, maybe some nucleotides are paired or unpaired, but it is not always the case. But it can try to help us, and we can use the sequencing technologies to try to detect the positions with these, when the chemicals can have reactivity with RNA or not. So how we can interpret this? So we can have the high reactivity. So when it is above 0.5. So, and we can say, okay, this part of RNA is flexible. And it can be probably unpaired. If we have the lower reactivity, we can say, okay, this one is paired or probably not so flexible. And there's some space in the middle. And usually people use this information to try to find the secondary structure. But it's not perfect. Okay, so where we are now with deep learning approaches for RNA structure prediction. If you see the last cusp, the best tool by far was thermodynamics-based with human intervention, not deep learning approaches. And the best one was vFold from Jijin Chen from University of Missouri. Recently, Rijudas organized a Kaggle competition for RNA 3D folding. And the best solution by far was, again, not deep learning approach. It was old-fashioned template-based approach. And in the final solution, the author submitted approach that includes combination between template-based approach and DRFold2, probably and arguably best tool for RNA structure prediction. But he found, and some people ask him, okay, what will happen if you use only template-based models? And he tried, and the results were better. So they achieved the TM score of 0.6. So we can use RMSD, but people in RNA especially like to use TM scores because they tell us more about the global fold. And what is the goal? We would like to have this score about 0.5, 0.6, that we can say, okay, this is really a good solution. Okay, so how we started to this field? So I moved to this field 4 years ago, and we just started with building RNA structure prediction, but we found that multiple sequence alignment tools are not so good. So we started to building RNA language model, so we built Renaumo, and at that time we showed for the first time that actually deep learning models can outperform thermodynamics model on secondary structure prediction. So on the left, you can see two thermodynamics-based model for secondary structure prediction. On the right, you can see some deep learning model, including RNA-FM, which was the first RNA language model. So, well, what is special about this data set? This data set is that we need to train using Li1 family out. And for test, we have this family, and then we need to predict secondary structure. So we just fine-tuned Renaumo, and we really show that it works. Of course, people complain, maybe you involved all of these sequences in building your models. Maybe it helps. It's sure it helps, but we really need to understand, and I hope people will start to think how we can interpret these language models. So we try to even bigger Renaumo. So the first one was trained only on no-coding RNAs because most of structures result are no-coding. But here we added coding ones, and we increase the number of parameters to 0.6 billion. The perplexity went down, but we didn't see any improvement in secondary structure prediction. So probably this is not the way to go, and adding mRNA probably does not help. So we also wanted to test and make a real test of RNA structure prediction models. So we developed a benchmark that we started with extracting chains from. Then we clustered with 90% similarity. It's pretty high, but we tried to do this. And then we filtered all of them which are older than January 2023, because the most of models we tested were trained on this data set, and in the end we had 84 RNA structures. And we tested and benchmarked on two data sets. The first one was RNA puzzle, and as you can see, most of these tools achieve some good results. But when we gave them a newer data set with very strict conditions, results are much worse. So much of RMSD is around 10, and we will be happy if we can come to 5. And as you can see, the best performing tool on the first data set, it's not the same as the best performing tool on the other data set. And AlphaFold was the worst one in both cases. So we also try to go one step further and try to say, okay, it is not enough that we have sequence similarity. Let us try to see if we can take into account structure similarity. And results are even worse. So yeah, RNA structure prediction is very, very difficult problem. So what we can do? What we have seen first is that when we look at these tools and the results by RMSD and by TM score, there is not always the single tool that performs the best. So what we did, we tried to see and compare, and on the last one, on the green one, you can see how the results would look like if we can select the best one. And we tried with two scoring functions like Rosetta and RS to see if they can help. They didn't. And it is what is interesting. Oh, I don't have here. Okay, sorry. Okay, so if you look for RS and AlphaFold 3, you can see interesting similarity in scores. It looks that RS prefers AlphaFold 3. You can see similar between tRNA and Rosetta scores. They also look similar. So for some reasons, these tools prefer each other. Okay, thanks. And so what we can do? So it is necessary that we increase the number of data because we don't have enough data. So we can use shape data, we can produce synthetic data, but we can also think if we can improve the scoring functions. The existing scoring function does not work well. And also at the end, since we are computer scientists, we will try to think about if we can find some inductive biases to improve our models. So we developed the home rank. It was a ranking function. So it is very similar to RS, and we used the original RS model to start. And we try to rank structures in accordance to their RMSD. So we just use molecular dynamics and change the original structure, and we know the rank. And then it was easy for the model to try to rank all generated structures. Also, on the other side, we tried to see if we can develop a new free energy. And why? So we believe that knowing something more about the structure can help us, and we would try to develop, and it's a work in progress, a free energy function that can help us, that we can use it as a loss. So it should be differentiable so we can train the models using this one. And also we are inspired by thermodynamics models who won the CASP, and we will focus on pseudonodes, some specific motifs in RNAs, and that was not involved in the previous functions. And as you can see here, this scoring function, it's really results from few days. I tried to push my lab that we have some results, so this is the best what we can do in few days. So energy rank function had the Spearman correlation much higher than RS and even than home rank what we tried with deep learning. Also, if you can see here, it is also, we were in hurry, so we don't use the same colors or something, but if you look the RMSD on the same previous structure, the energy rank was the lowest, and we had, it is the last one on the right, we achieved a higher TM score than other function scoring or ranking, but still it is not enough. So if you remember, we want to achieve above 0.5. So we also built our own RNA structure prediction model. We call it RAFO, and it is actually a nickname of Rafael, a PhD student who did this and who did Renaumo. So we use two kinds of information. We use a language model and we use secondary structure prediction to, and the rest of design is actually similar to AlphaFold 2. So yeah, we use evolutionary information from Renaumo. We use, for training, integrated function elements. So we take the parts of RNA that have some kind of function together, so it can be a few chains, it is not one. And then we use some positional encoding similar to AlphaFold 2. And finally, what we try to do, we try to use structures achieved by V-fold as the distillation. So we have 1,000 structures from PDB actually extracted from these integrated functional elements, but we added 700 structures predicted with V-fold, the tool which was the best one at CASP16. And we also tried with shape data, and it didn't help. And we tried to use the templates from the winner of the Kegel competition. It didn't help. Maybe if someone of you can help and produce better results, it would be great. So you can see here, we have comparison between, on the y-axis, it is original RAFO, and it performs similar to DRFold 2. And on the y-axis, you see results when we use this distilled data set. And for some sequences, results are better, but for some are worse. It is interesting, this one, and it was outlier for CASP16 because it was the structure that had very similar structure published before. So on the right, you can see results for template-based only models. So they achieved the 0.6 TM score at the Kegel competition, but here you can see only the best results. So they predict the 5 templates. And if you look at them, for some it can help, but we don't know which of these 5 templates is the best one. And I'm close to time, so adding templates by using the same approach as in AlphaFold 2 didn't help us because many templates are actually bad. Distillation slightly improves, but not much. But we have just started. So as I mentioned, we started with de novo assembling 12 years ago, and now, together with other teams in the world, we moved the field. I hope we can move this field as well. So on the left side, you see the members of my lab, and the right side, we see collaborators. Among them is Wan Yue, who is RNA biologist, and Sikic Chen from University of Missouri, who helped us a lot. So yeah, we have to thank our sponsors. And if you like to come to Singapore, we are hiring. We have open positions in RNA structure prediction, optimizing mRNA, and various kind of DNA language models. Thank you. I was a bit out of time, and yeah, I'm happy to answer your question if there's a time.
All right. Hi, very interesting talk. I'm very curious at when you said that you tried to train with the shape data and it was not helping much. I also saw at some point that shape data should contain rich information. It's a great source of data. So I wonder if you have some intuition why it didn't help that much.
I have no idea. So the shape data is mystery. And we tried for secondary structure, for tertiary structure. So we created shape data for known structures from the PDB in vitro, and we also tried in vivo. And so far, we have not seen any improvement. So, it is always a naive assumption that unpaired will have the high shape per activity, paired will have low, but this is not the right true. And now we inspect shape data and really try to understand what kind of information they provide. Some other structural probing methods are even worse, but please don't tell to RNA biologists, they will kill him.
Hi. Actually, maybe a follow-on onto that. So there was work from the previous year with the DOS lab on their chemical probing to use as like a pre-training method. And then at Atomic, we've also reported success using this method as well. Maybe a follow-on is this like, did you attempt to do something similar to the DOS lab and it was just not particularly successful using the shape dataset, or?
Can you repeat? What's the question? Sorry, I didn't get it.
I think you mentioned that you didn't see much of a lift from using shape data, whereas previous groups seem to have had some success using this as like a pre-training paradigm. Was this something that you tried and just didn't found successful in downstream 3D prediction, or could you talk about that?
So we tried to add directly shape data in the prediction, and it didn't help. We also tried Ribonanza Net prediction, develop another Kaggle competition organized by Rigidas, and it didn't help at all.
Thank you. And then I think a separate question is that previously it was pointed out that RMSD is often a very tricky metric for RNA. You can get high RMSDs, but really great local structures and vice versa. A lot of these comparisons were looking exclusively at RMSD, and AlphaFold was doing almost shockingly poorly. I think some other works have shown like LDDT or TM score adjusted, and AlphaFold is much more competitive. And do you have any thoughts on like, is RMSD the right way to rank these models and how much it influenced your results?
Yeah, it is a good result. So it's a good question. So, RMSD, it's really prone for some outliers. So if you have in local structure something that is far, because of the quadratic equation, you will see a huge increase in RMSD. So that's the reason why TM score is better. Regarding AlphaFold 3, we really didn't see much improvement. And it was interesting what we have seen when we try to say something positive about AlphaFold 3 is that when you try to predict, because many of these chains are actually chains in complexes with proteins. So if you look them in the complexes, and then extract chain, AlphaFold 3 performs better. But still, at this moment, I think DRFold 2 is the best tool in accordance with RMSD or TM score. Thank you.
Thank you, Mile.
I'm not sure if we're at the point where this is a viable strategy, but I was wondering if there might be possibility to use data of just like any molecular structures outside of RNA and then try to apply them to RNA, like with transfer learning. So like, I mean, I know that you found that AlphaFold was not very helpful, but I was wondering if like protein structures, DNA, or like other materials, like if just all like potentially applicable structures could then be used in transfer learning since there's such a lack of data?
It's a great question. So, as I mentioned, we will try all kinds of dirty solutions. And even in one moment when we tried, and we played with RS, we tried to see if we add the protein structure, because at the end, atoms are atoms. So if they can help us. Unfortunately, we see maybe slightly improvement. And so any kind of trick is more than welcome. And it should be the way. And I really like that this structural probing data works because they will be most easiest way to achieve. And maybe some people, I had discussions with Riju and he told that if we have enough money, we can learn everything from shape. But yeah, we need to find money. Okay, thank you.
Money seems to be the problem. Thank you, Mile.